Welcome to The Explainer. Today, we are digging into a really fascinating paper that uncovers this hidden, kind of weird flaw in AI. It helps explain why even our most powerful models can act so strangely sometimes. And it all boils down to this one thing they're calling the squeezing effect.
All right, let's just jump right in with the central mystery we're tackling today. So you've got this super powerful AI, right? You give it extra training, you're trying to make it better, align it with what we want, but then instead of just improving, it starts doing weird stuff. It gets repetitive, or even stranger, it actually becomes less confident about the right answers. So what on earth is going on here?
And look, this isn't just some random glitch in the code. No, it's a really deep, kind of counterintuitive problem that researchers are just now starting to get their heads around. It's this paradox that's sitting right at the heart of how we fine-tune these massive models.
So, to crack this case, the researchers knew they couldn't just look at the finished product, the fully trained model. That wasn't going to cut it. They had to watch it as it was learning, step by step. The paper has this great phrase for it. They needed to understand its evolution from a dynamical perspective.
And to see what's actually going on under the hood, they pulled out this really powerful tool called learning dynamics. Think of it like putting on a special pair of glasses, right? It lets you see exactly how the AI's brain is getting rewired with every single new piece of info it gets.
So what learning dynamics really does is it lets us watch how knowledge kind of ripples through the AI's entire network. Like, when you teach it one specific thing, how does that change how it feels about, well, everything else? It's not just about memorizing a single answer. It's about understanding this whole web of connections between different ideas.
Okay, to make this all a bit more concrete, let's use a classic example that I'm sure you've seen before, teaching an AI to recognize handwritten numbers.
Now, this is so important. What we're seeing here is the AI's point of view. For you and me, a 4 and a 9 are totally different, but for the model, it's just looking at pixels. And from that perspective, they share a lot of the same features, right? There's a vertical line, there's a loop up at the top. To the AI, they look really, really similar.
And this just perfectly illustrates that core idea. So when we show the model an image and we say, hey, this is a 4, its confidence in the number 4 just skyrockets. That's that big blue bar you're seeing. But, and this is the key part, look at the other bars. Because that 4 looks a little bit like a 9, the model's confidence that it might be a 9 also gets a little boost. See? Learning one thing creates that ripple effect we were talking about.
Okay, so that ripple effect is absolutely key. Let's hang on to that idea. Now, we're going to see how that exact same dynamic plays out when we're fine-tuning these huge language models, because that is where the real paradox shows up.
So there are basically two main flavors of fine-tuning. The first one is called supervised fine-tuning, or SFT for short. This one's pretty simple. You just give the model a prompt and the one correct answer. It's like showing it the answer key in the back of a textbook. The second method is direct preference optimization, or DPO. This one's a bit more subtle. You give the model a prompt, a good answer, and a bad answer, and you just teach it, hey, prefer this one over that one. Kind of like a teacher grading two different essays and saying which one is better.
And it's in that second method, that DPO preference tuning, where things start to get, well, weird. The simple act of telling the model, this answer is bad, creates this totally unexpected and frankly harmful side effect. And this is what the researchers have named the squeezing effect. This brings us right to the heart of the mystery. When we tell the model, nope, that answer is wrong, it obviously lowers its confidence in that specific answer. But here's what the researchers noticed. It also started lowering its confidence in other good answers too. So if the probability for all these options is going down, where is all that lost confidence going?
And here it is. This is the big reveal. That negative feedback, it doesn't just spread out evenly. Nope. Instead, the model takes all of that lost probability and it funnels it. It squeezes it all into the one single answer it already thought was the most likely. And get this, even if that answer wasn't even part of the training example it just saw.
So what does this do? It makes the model's internal map of possibilities really peaky. That's the term they use. It becomes ridiculously overconfident in one single option, and it just loses all nuance about any other plausible answers. And this is what causes the model to get repetitive or super generic. It's just defaulting to its one single highest confidence token over and over and over again. And the effect is even worse when we tell it an answer is bad that it already thought was a long shot. The shock to its system is just too much.
Okay, so we've found the culprit. We've diagnosed the problem. And the fix that the researchers came up with is, well, it's brilliant. And it's also completely counterintuitive.
At first glance, the solution seems totally backwards. The idea is, before you tell the model that the bad answer is bad, you first teach it that the bad answer is, well, plausible. So here's how it works. Instead of just showing it the good answer, you first use that SFT method to teach it that both the good answer and the bad answer are reasonable options. Then, and only then, do you use DPO to say, okay, now prefer the good one over the bad one.
So why on earth does this work? It's all about softening the blow. By first making the bad answer seem a little more plausible to the model, the negative feedback that comes later isn't such a huge, jarring shock. It's not this super unlikely thing getting punished anymore. And this lets the model learn the preference much more gracefully without totally overreacting and squeezing all its confidence into that one single peaky spike.
Okay, that's the theory, but what does it all mean for actual performance? Does this clever little trick actually make the AI better? Well, the numbers speak for themselves.
So the researchers put their new extend method to the test against the old way of doing things. And they had other big AIs like ChatGPT and Claude act as the judges. Now, take a look at this table. At the very beginning, at 0 epochs, their new method is actually losing. And that makes total sense, right? We just taught it that bad answers are plausible. But just watch what happens after only a couple of rounds of training. It just dramatically pulls ahead.
Yeah, at its peak, this new method hit a nearly 70% win rate against the standard way of doing things. That is a massive, massive improvement. And the best part? It's not because they used a bigger model or threw more data at the problem. It's just from a smarter, more nuanced understanding of the training process itself.
And ultimately, this is why this research is so important. The squeezing effect is proof that the path to better, safer AI isn't just about scale. It's not just about making them bigger. It's about deeply understanding how they learn. And it leaves us with a pretty critical question, doesn't it? If the best way to fix this flaw in an AI is to first teach it that a bad answer is plausible, what does that tell us about the nature of teaching itself? Not just for machines, but maybe for us too.